Hey guys, this is Jaser. Let's have another LeetCode problem today. It's 3433 minimum genetic mutation. A gene string can be represented by its character long string, which is ACGT. Suppose we need to investigate mutation from start to end, where one mutation is defined as one single character changed. So AACCGT 2, AACCGTA is one mutation because only the last character, T, is transformed into A. There's also a gene bank that records all the valid gene mutations. A gene must be in the bank to make it a valid gene string, okay? Given two gene strings, start gene and end gene, and the gene bank, return the minimum number of mutations needed to mutate from the start gene to end gene. If there's no such mutation, return -1. For example, ACCGGT, ACCGGTA, the bank is ACCGGTA, so we can just transform with one mutation. The other one is ACCGGT and ACCGGTA. So obviously there are two changes, right? We can transform into ACCGTA, maybe this one, and then we can say AACGGTA. So there's two mutations. So the minimum is 2. So yeah, so for this kind of thing, because there might be all kinds of orders, right, in the mutation from the bank. So we can basically traverse through all the possible mutations to try all of them and to see if the end gene is there. Yeah, and that actually, if we think of all these gene as a node in a graph, we can actually check if there's an edge between two nodes by counting the character differences. So if there's only one character different, then there will be an edge. If there's no, then if there's no, then there's no edge, right? It is said that the starting point might be included in the bank or not. Let's suppose that it is in the bank. We're using, okay, anyway, we would we will put all of these in the should we? No, we should not put the end in it. We should put just the bank plus the start gene in it, and use this list to form a graph. But we need to dedupe. Anyway, we need to dedupe by simply check if this gene string, any of the gene string, is the start gene. So once we formed the graph, we will start searching, right? Traverse. It's called traverse or traverse. Traverse, I guess. It's traverse through the graph. Because we're going to get the minimum mutations, we're doing a BFS fashion. So we will start from the start gene, and then gets the next round, gets the next connected graph, the gene, into a queue, and process them and increment the steps, mutation count by 1, and then do them over and over again. There needs to be in order to prevent that the infinite loop, once a node is processed, we need to once it's processed, we need to put it into a visited set, and that's our plan. Cool. Let's do it. So the first thing is we will define it. Do we need to know? Oh yeah, we need to actually define the node. Wait a minute. How can we define the node? Yeah, we need to define the node actually. Let's create a node. Constructor gene. This gene equals gene. and also the mutations. We create a set for it. This set should hold the node. Do we need to? Yeah, I think the set is good. Okay, cool. And we would construct a graph. And also we need to, yeah, so what does the graph? We would, okay, how should we do this? Well, start gin is actually the node, and for bank, we'll create a node for the start gin. Yeah, and then for bank, for each item in the bank, we would first we check if it is the start gin. If not, we will create a node for them as well. And we would okay, we would add every gin in the bank to we would add every gin to calculate them, right? Calculate their differences. And if now create a node for them as well. Yeah. Okay, so let's just create a set for it. So first, a gin set, new set. This is start gin bank, and for this one, and we will get the gin out from this set and create the graph. Cool. But how we can get the node? We actually need the map, right? Gin map. Yeah, gin map for gen of gin set. We will create a node. Okay, I see. Yeah, let's create a function called get or create a gin node. No, gin. If gin map has gin, just return it. If it doesn't, we will create a new node. Gin map set gin node, and also return the node. So by this, we can just use this function to get the node lazily. Okay, so for each gin, we will get a node. Get node gin. And then we will get the node, and we will check the distance. Oh, wait a minute. This is not where we don't need to actually to check all of them. We can actually avoid duplicate, right? So we don't need this actually. Actually, we don't need the gin set, maybe. we can actually say all gens, just put the start gen in it and bank in it. And then for let's traverse these gens array. And we will do the comparison. So for let j equals I plus 1. This one is -1. And we will count the difference. Let's say function is mutation AB let diff count yeah, okay, if A and B is the same, A equals the same, also return false. So this means that we will skip the node. Okay, so yeah, and then we say if this could be a mutation from James I and James J, and we will set them up, right? So node I get or created James I, node J, and then we will set them up. So this one, what is that? So mutations node J, and node J mutations at node I. Great. Now we'll just start the BFS, right? Let's put the node in the again we need to create a visited new set. Also we need to put a queue there. We need to put the queue there, which is get or created start gen. Okay, and then we'll use the result like a step count, mutation count, 0. Okay, while the queue length is there. Okay, const length. We'll get layer by layer. So this we can use the let. Okay, while length make it at 0. Well, DQ. We can actually wait a minute. Yeah, okay. Const head equals Q shift. If this one, so we check this one. If this head dot gen, if it is the target, which is the engine, then we already found it. So we just return the mutation count, right? Yeah. If it is not found, we would push. Wait a minute. And then we would actually push the visited. Push the head. And push the connected nodes in the queue as well. So for node of head mutations, just mutations, yeah, mutations. If visited has node, if it is not visited, we would push the node into the queue, enqueue it. And once this is done, this means the one layer of nodes is handled. So we would increment the mutation count +1. Eventually, there is no. If we couldn't find any target, then we return -1. I'm not sure this. I'm not quite confident about the code. Let's just try to do this again. So, first one, we get or create. If this gem has it, we get it. If no, we create a new one, set it. Yeah. And then we will start from this 3. There are duplicate here. Might be duplicate here. Bank. Okay. Then we will compare all the pairs. Yep. And if it is mutation from I to J, by commutation, we will check the difference count. If it is bigger than 1, false. Otherwise, it's true. So yeah, if it is mutation, we will connect them. Yeah, in 2 ways. Yeah. Visited the queue. We'll start from the start gen and do it in a BFS way. So you can see we check the length and we will get all the items out. So see if it is our target. If it is, we found it, the mutation count. If not, we would push into a visited. Then for its connected nodes, we would push them into the queue if they're not already visited. Yeah, and then negative increment the mutation. I think it should work somehow. But yeah, there might be errors every time. Ooh, cannot read property of undefined. Reading at mutations. Yeah. Okay. Typo. Again. Reading 0. Undefined. Use mutation. IJ is not right. I is J, I +1. Oh shit, it's J. Okay. Again, visit the push. Oh, it's not push, it's add. Man. Come on. Accepted. Not sure. Okay, come on. Yeah, I think it works. Maybe it's not the fastest. Okay, I guess that's it. Maybe let's see the fastest one. Oh, okay, neighbors. Q visited. Q. Okay. 0. What does 0 mean? Visit start gen. Get neighbors. Node bank. Get neighbors. Okay, I think basically idea is the same. Maybe there are some minor improvement. But anyway, that's all for this one. Hope it helps. See you next time. Bye.